Okay. Good morning, everyone. What is this course about?
Making phone applications and try to look not dumb.
All right. The latter part is the most important bit, right? So yeah, work on that one. That's the important bit, yes. So phone applications and try and not look dumb. That's interesting. I understand you so far have gotten as far as to look into UI, I believe.
Yes.
Is that correct? You have completed that. So Mariusz can't be here this week. That's why I'm interleaving this whole session a bit. Because he's in Trondheim. But I understand you have some lab tasks you need to do, right? Or yes, no?
Exercises.
Exercises, nice word, good, sounds good. Exercises will do. And you have learned about UI. What kind of types of UI did you talk about in the tutorials? Yeah?
We talked about a lot of different view groups that you could use to lay
View
out.
groups as well. Okay, I didn't know that. Okay, right. So
we did linear layout, constraint layout.
yeah.
We had some group work so that everyone would read one of the layouts and then present it.
Okay, cool. So you kind of have an exposure. So all the layouts are kind of covered?
Sort of. Yes.
Sort of. Okay, UI is fine. So you should be prepared to do actually the exercises, I guess, right? More or less important. So that gives me enough reason to disrupt the flow in my natural fashion, and that is to look into a slightly different subject for two reasons. Number one, we need to have more theory questions in exams. Number two, it's something you come across later on again anyway. Number three, we didn't cover it in cloud. So, because some of you took that course, how many of you have a drift background, operations background? Yeah, that's scary. Good, yeah, okay. For you, it will not be super exciting. How many of you, well, you know, so that's the price you pay, but you know, that's about, what is it? I would say 7%. How many of you have an idea how networking actually works? Yeah, cool. Yeah. So based on operations, I assume? On
Practice like 6-7 years ago.
Oh, okay, interesting. All right, and did you? Private interest or?
This is my second degree, so.
Okay,
Yeah.
right, okay. So we're talking to a senior, yeah? So, okay. So part of the reason I think US wearing students need to have, of course, some networking background. May not have guessed that throughout the degree eventually. And whereas the people that came before you actually had this background as part of the curriculum, the ones after you will have it as well. But you seem to be the only one that have kind of gotten out of this, right? Or did you have any networking course in programming? No, right? Good. I'm not saying good here, but I think it's important to see some of the foundations, and again, they are relevant for mobile as well. And I'll probably ask that question at the end again. You tell me why. Oh, why is networking relevant for mobile? More generally, perhaps more specifically later.
To communicate over the cloud.
Yeah, there's some communication going on all the time, right? So, point is, your end device is kind of a bit dumb in the end, right? So it's just an endpoint device. You may have some, 3D performance and so on, but fundamentally the value you draw out of it comes from the ecosystem, right? Be it apps, games you can play, and so on. So communication, by whatever means, is always necessary. Be it Bluetooth, Wi-Fi, of course, or your cellular networks. And one thing that always reminded me of this one, I think in around 2011 or so, the first Android smartphones came on the market and were actually really quite popular. And they were running Android, I think 1.6 if I recall this correctly, or playing around with those. And at that time I was living in New Zealand there and developing this on those phones. And they constantly made the assumption that you have internet connectivity. And in some parts of the world, guess where, that's not necessarily always the case, right? And that reminded me very, very strikingly that firstly, you shouldn't necessarily always assume internet connectivity, but fundamentally, smartphones were built with this intent, right? They're not meant as isolated end-user devices. They're meant to be used in a kind of networking setting in the widest sense. Yeah? So there's, of course, certain cultural bias was, I suspect, in the development, but it's really important to think about networking as an integral part of doing mobile development in the widest sense. And of course, there's ample support in Android, iOS, and so on. And in Android, it's particularly pronounced. But in order to do that, there's certain aspects that you still, I guess, need to know from the theory side before you enter the networking bit. And the two major things there include threading. Have you talked about threading? No? Yes, perhaps?
Mobile, no.
Not in mobile? Okay, so it should be in mobile as well because it's specific in Android. So you know how the multi-threading models work here is slightly different. And of course then a lot of APIs you get on top of that. Yes, so that's something we'll talk about. But what I want to go back to is to seed you a bit of a background in the network principles in general. So you kind of contextualize whatever you learn later, and there will be another session on networking, whoever gives it. To contextualize clearer, you know, what networking means and what you're actually doing, what you need to be concerned about. And general understanding, because that's, I think, what people would expect from you in the practice, at least to have to know the endpoints you're dealing with that are relevant in a network. All right, let's get into it. Some networking fundamentals I want to bring in here. And the fundamental question is actually, how does networking actually work? The ones, you know, networking you use when you use your mobile devices. How does it actually work? I want to hold you off a bit, those four guys, but have the rest of it perhaps give some intuitions. And if after 10 seconds there's no response, then I activate you and you're invited to chip in. Please, I have not seen you, sorry.
We're talking specifically about mobile devices, right?
Well, not necessarily. Well, network in general, including mobile devices, yeah?
Right, so there's a huge network over the world
Yep.
with cables and all that.
Okay,
And then
I like that one.
if we're talking about mobile devices or laptops, for
Yep.
example, they connect to the nearest point using electromagnetic waves. So basically 4G or whatever is available. And then from that, after the data has been transmitted, it just goes through every wire, you know, well, not every wire, but the shortest path to get to where it's being sent.
Wow, okay. So there's two challenges in there, yeah? You're highlighting, right? So on the one hand we have, what are those two challenges?
One of them is routing,
Yeah.
so you need to know how to get to the point and not get lost in
Yeah.
a loop.
Yeah.
And the other one is keeping the data safe.
You're right, yeah. Security is an important aspect, but that's it further on top of it. You mentioned something else before. So on the one hand, the information is transmitted via cables, right? But also by waves, right? So, so we have different media. So the challenge there, and you highlighted very nicely, is that you need to be able to facilitate the big network, also we call it internet, I guess. You know, to facilitate end-to-end communication. So you can use Firestore or all the services you want to use in your mobile device or where you want to store your data. And of course also to communicate, but in principle you want to be able also to communicate across different devices and device types. Shouldn't matter if you're connected via cellular, via Wi-Fi, if you're connected via cable with a laptop, for example, and you want to interact from between phone and laptop and so on. In order to facilitate this, you need to find a way of kind of bridging those gaps, right? Because not everything communicates, as you said, the same way, let alone the communication problem that routing is up. I think you really highlighted the main two challenges in a good sentence, in one sentence. Okay, well, bring it closer to home. Let's say we're writing an email. How is that actually sent over the wire? You know that, right? You guys? Who wants to break it down? How does it actually work? What happens if you send two emails when they're sent at the same time? How do you avoid problems with this? Please, you have a point. Please. That should be this whole thing. I think you're on the right track, yeah? So you have an email sent to the server and then?
Then the server sends to the person to the best.
Okay. Right. Okay. Overall, you're right. Logically, you're correct. So basically, it functions like this. You send an email that is connects to some server, right? So this server finds the other person's email server, right? So for example, if you send from MTU to a Hotmail address or whatever's in nowadays live address, then it ends up on this live server, and whenever the person checks it or has push notification activated, it will eventually appear on their endpoint device. But what I want to get is it's the question rather how it's broken down. How to get to the wire before we do this fancy sending via the internet. And that's the point of this talk here. So fundamentally, when we are dealing with data, I mean, the key point that you're probably always facing as a prototypical computer science graduate, when faced by friends that don't really have the deep insight, they may just always suggest that everything is represented binary in a way, right? So 0, 1, 0, 0, 1. That's the basic understanding that people often have when it comes to your discipline. I'm not sure if you had that experience before. No, you're lucky. Or you're just mingling in the wrong crowd, or the right crowd, who knows. So that's good. But fundamentally the question is indeed, so we have this email, and we want to kind of represent it on the wire. And the wire basically differentiate between two states, you know, power or no power, basically, right? So signal or no signal. And based on this, the idea is to, okay, how can we reconstruct this email on the other side? Sounds to some extent a bit magical. Well, it was, nowadays not anymore. But so let's get to it, how that could work. Well, it actually builds on two principles. Or the whole idea of networking builds on two principles, and that is the idea of abstraction and separation. You may know that from another programming paradigm, but fundamental to the idea is that communication happens across layers. So when I communicate to you, there's multiple aspects that are involved, right? We have endpoints of communication, right? If we're talking, for example, we have a medium of communication, which is suspect air right now, right? So you are hearing, processing the audio output I'm producing, and there's of course the message content, meaning we need to have a shared language to do that, right? If I communicate in Norwegian, that's getting very funny, and that is not the worst thing. The worst thing is probably that the content will not get across, or not accurately across, right? There will be ambiguity introduced, for example. And those are different forms of abstraction layers as well, but in computer systems they're quite differently organized. So fundamentally at the basis, you have the data, which is, let's say, the message, right, that you want to deal with. And in order to kind of embed those different layers, you know, infrastructure, the endpoint representation, and then the actual application level content, you kind of need to nest those in using the means of abstraction. And for this purpose, in networking, there's always to talk about PDUs and SDUs. Do you guys remember those? What are PDUs? Is anyone acquainted with those guys and wants to elaborate? Please. Yeah, please.
PDUs, for example, the IP packet.
Yeah.
So that's the frame in there too.
Yeah, that's correct. Yeah. So you mentioned that the IP header, for example, is part of this PDU or a frame. So we get into this one. But if you were to use the real world metaphor when you talk about this, PDU, SDU, as opposed to the specifics, because you are pretty deep in the weeds already, specifics, what would be a good metaphor in real life that represents SDU and PDU?
A box. Put a box inside a box, inside a box, inside a box.
Yeah. Just some, yeah. Is there anything particular about the box?
It has addressing saying that it's supposed to deliver in this format and to this place.
Cool. Yeah.
And some other random data.
Random? I'm not sure. We started random is scary, but yeah, systematic, but data, right? Meta information. So you're right. So it's the fundamentally the packaging and unpackaging idea is absolutely spot on. The key aspect is there's some sort of envelope, some descriptor on this thing. So I liken it often to a letter. You know, so you have envelope, letter, you have content, and you have the envelope, which in itself doesn't have content, right? So it doesn't have meaning. You can throw it away, but what its purpose is to address the packet accordingly. And that's very much the same here across multiple levels and layers. So that's why the package and package idea, we get into that. But so abstractly, we have the protocol data unit, which describes, for example, addressing information on a given layer. We get into that. And more information of what the nature of the data is that's inside its package. And then the SDU, which is effectively just the payload, right? So whatever you want to encode there, it just needs to be described with respect to where it's coming from, where it's going to, and how you deal with this information to some extent. So, and how this function fundamentally looks like here, reasonably concrete already, is that, yeah, you mentioned frame already, for example, that we have different, well, data that, for example, includes meta information such as, let's say, source port, destination port. We'll get into that later again, in one sort of package, right? So, and from the perspective of one layer, this one here would be the protocol data unit, and this one would be the service data unit, the content, the payload. However, when we then embed this in a higher level package, that's where the box inside the box idea comes in, and we get to this meta information later, there's a different form of addressing that's relevant. And from the perspective of this higher level, this bigger box, if you like, this smaller part here becomes its SDU. So suddenly the protocol data unit, the information that says something about the payload sent across, is in itself becoming payload, right? And that happens across multiple layers. So the principle is always the same. And we'll break down those different layers and see how they make sense and why they make sense. But understanding this encapsulation idea is very important, right? You have a package that is labeled, has addressing, and is then packed into another package which has label addressing, which is probably packed into yet another package. And at the lowest level, it hopefully comes out this way. And how this works is something we're gonna look into a bit. So, coming back to the idea. So we have abstraction and separations of concerns. We have some sort of payload data that we're going to encode. But one of the challenges is there, we need to label those data with respect to some information that carries information about whom to transport it to. Really the endpoints, the endpoints really of a particular service that they can consume the data. And fundamentally, the idea of this initial step is to look at the data and bear in mind, can data package be of arbitrary size? No. Yes? Hard to say. What's the trade-offs? Can they? First of all, yes or no? And what's good about it and what's not so good about it? Please.
A problem with having large packages is that it takes up much space of the wire, so it gets hard to, or it's only one thing can communicate through the wire suddenly. Which causes a problem with multiple users exist on the network. Yeah.
So what would be good, however, I'll come back to you in a second. What would be good if you could communicate one large package over the wire? What would be the advantage of doing so, though?
You would eliminate more headers, usually.
Yeah. Right, so the efficiency increases, right? So just to give an example, assuming you're downloading a movie, right? So, and people don't do that anymore. So you download something, same, you download the GitHub repo, you need to have one consistent file, one zip file anyway, right, that you're downloading. And this file is considerably large. Well, if you can ideally download this file in one go, right, so you only have one set of complexity in terms of those headers, right, because you only have, yes, the payload data is basically the full zip file or whatever it would be, and then one header. If you split this thing up, necessarily, of course, you have a partial payload, partial payload, partial payload, but not only that, of course, you have a fresh header for each of those, right? Because at the endpoint, it needs to be kind of communicated, okay, what is this? Is it part of a zip file or whatever it could be? And that's something you just suggested there. So, and necessarily it becomes more inefficient, right? But again, conversely, it puts quite a bit of load on the wire if we expect one package to go through in one go. But I'm coming back to you, but you had a comment.
Also, if the data gets corrupted, we would have to send the whole thing again.
That's the main point. So even if you send in a huge package and hopefully it works out, you may cause some people to wait. But worse, just imagine you're downloading this 300 megabytes package, and after half of it, there's some interruption or some errors introduced or whatever else, right? Then this entire package needs to be resent, right? There's no way of partial resending, because one package is the kind of atomic data unit, the smallest possible data unit. So that's also one point there. That's why, for example, that's why downloads are basically interleaved into multiple smaller chunks. You had a comment.
Yeah, that was
On the same page.
yeah, and you could also it couldn't get there. It can also not get there at all.
Exactly. That's another thing. Exactly. So that's specific to the networking routing problem kind of thing, right? So we need to deal with the fact that things may not necessarily reliably flow from one party to another because we're working over a shared medium, right? So we're kind of as we are communicating outside, and you probably know, for example, here in a class setting, usually you have the convention that's one person talks, right, and everyone listens, and so on, conversely around. If we all were chattering at the same time, there would be no information getting across anymore, right? There would be a lot of noise, but it would be very hard to pick out the signal, let alone the multiple conversations that we'd have. And that's the kind of challenge we face de facto on the internet as well, because it's kind of a public space. So, but unlike here, we can clearly say stop. It's really hard in a decentralized medium. So there needs to be other ways of ensuring that the data gets across, even though there's a lot of chatter. And how this is done, we'll hopefully understand better in a bit. So, coming back to the idea, large package, small package. Was there anyone else who wanted to comment on this? I hope I... Yeah, you have a comment?
Could you just repeat the disadvantages of sending?
The disadvantages?
Yeah, of sending the entire package.
Yes, yes. So the disadvantage of a large package, as I mentioned over there, is twofold. Number one, it blocks the communication channel, right? So if I send a long blah 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 blah, the communication channel is blocked, right? There's no chance for anyone to interleave, you know. So practically, but worse is the situation that you're sending information and it gets corrupted halfway, right? So you have a huge image in, you know, 1 gigabyte. Whatever, video or whatever else, and gets corrupted after 800 megabytes. You need to start again. So, you know, just imagine the annoyances and the load it puts on the network. That's the main argument against it. The main argument for it is, of course, the increased efficiency, right? Because you're sending the payload data, so maximizing the network channels used for the payload data without interleaving it with, you know, packet headers, the kind of stuff we just talked about before. So it's a trade-off, and we get to that how it's actually resolved. Please.
What is it that decides to send it as a big package or small package? What is it that?
Correct.
What is it that decides?
Yeah. So to some extent, the specification. So because there are certain limits specified with respect to package sizes, because the challenge is we have the internet, we want to use the internet, right? And over the internet, we want to communicate across different devices. We get to that, and so on. Uniform packages, right? So you want to, in principle, be able to send from your mobile device some sort of data to a desktop device, to whatever other endpoint you can just imagine. So there's a certain need for standardization. You can't just say anything goes. You know, you just pick up your package size. In practice, so within those boundaries, there's the option to reconfigure it depending on, of course, the kind of medium you're using. Get to this, but more importantly, the routers in the network will decide what package sizes they support. They'll just say, I only support package of that size. Send anything bigger, good luck, right? It will not reach the endpoint. If you send anything smaller, sure, go for it, right? So then it becomes again inefficient because you need to know those sizes. But they're usually fairly standardized. You can modify it, and there's sometimes sensible reasons, for example, within organizational network for doing so. For example, you want to, for example, if you have a network that suffers data corruption quite a bit, you kind of want to force, you know, at least temporarily until you fix that, perhaps reduce your maximum transmission unit, the so-called MTU. But this can be done in-house, basically. But when it comes then to the public interface, sure, you may send out smaller packages than necessary, but at least you get them sent out, right? So there is a certain discretion, but fundamentally it's based on standards. And I get to the exact package sizes in a bit, just to give you a feel what we're dealing with in practice. You will not see much of that, I think, in person, but it's good to get an intuition of how much data you can actually send. So very good point. It brings us to the essential challenge here. Imagine you're sending a large, sending an email that includes, for example, attachments, right? Multi-megabytes. In principle, that's possible, right?
Yes.
Just checking if you're awake. Okay, good, thanks. And we have a limited amount of data. Well, one of the ideas here is of this particular initial part is actually to chunk up those data, right? So take the payload, the full attachment, what is this, or video I mentioned before, and chop it up into individual packages, and then give all those individual packages a individual header. And the header basically says, well, I might actually package 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of n packages. Well, it's not infinite, k packages. So, and then the idea is, okay, now we have the packages decomposed, they're all set out here. Okay, we need to send them over the wire somehow. But it further needs to keep some information. Okay, what's the nature of the data inside there? Number one. Number two, what's the endpoint that it communicates with? Or rather, how it's addressed within a particular, basically which application will it use on the endpoint device. So if you have imagine you have an email program sending this out. Well, on the receiving side, guess what? It's most likely an email program that's supposed to be dealing with this. Right, not your browser, or not your whatever other tool you're using, video player or so on. So that's something that's embedded there to some extent. We get to this slightly more explicitly in a bit. And in addition to this one, so now it becomes messy. So this was the service data unit, and this was the protocol data unit for the layer we just discussed. Right? And this compound thing here now becomes the payload for the next higher level. And in this case, when we add a so-called network layer. What does the network header? What does the network header do, fundamentally?
It contains the IP address of the next router or the next entity is going to go through.
Yeah.
So it's going to give to the next device.
Yeah.
That device can see it. And the next address is going to go to and send it to
yeah. Cool. Yeah, that's right. So here it's really about, that's the essence, about identifying nodes, right? Nodes on a network, like machines, routers, whatever else, devices generally, right? That's the intuition. Whereas again, the earlier one, this header, was responsible for dealing with applications on machines. You know that about port. Did you guys hear about ports before? Not you guys, but the rest? You are comfortable with ports, you are also. The rest, are you comfortable or not? That's something that's, we'll come back to that. Good. So this is application level, telling you where on the machine. This one is which machine in the first place, right? So just to step it back a bit. And then we have one more, just bring it in. You mentioned it before, the frame header. And even though we know which nodes or endpoints we want to address, there's still this thing about the actual infrastructure we're using, right? We're sending stuff over the wire. It may be the wire, but it may also be over the air, right? So using wave protocols and so on. In order to accommodate this, of course, we have yet another set of different protocols, right? The network package size may vary depending on if it's cabled or non-cabled. We have different standards for networking, older, newer standards, please.
The network area, they don't quite understand it. It's kind of vague. So you have an IP address, which is yours, and then it contains the IP address where to send the package to.
I go into the package in a second. I just want to motivate the high level first.
Okay, and then I didn't understand the network area.
We get back to that in a bit if you want. I mean, yeah, we get back to that. It's probably makes more sense because I should actually show the headers with all their messiness. But fundamentally, at the lowest level, it's really about the hardware you're using, right? So please.
The frame header has the MAC address of the local, so it's going to go to, so that it will be sent to the people get the local network, for example.
Yeah. So, but fundamentally, what's the other term for MAC address? How do you sometimes call it as well?
Physical.
Yeah, right. Physical address, because it's fixed to the actual device, right? So, and then we have a logic address, which would be the IP address, which can be changed. You guys know that, right? Every time you go into a different network, most likely you end up with a different IP address. So, but fundamentally, this is tied to kind of the more or less to the hardware, to the infrastructure that you're actually using when you're transmitting data. And there are different protocols, and there always have been different protocols over time, and there will be different protocols, because every few years you realize, oh, I need to upgrade my network router, because it's, Wi-Fi, because there's a new standard coming out. Next one we call is Wi-Fi 6. Did anyone read up on this? Yes. So it's the next big thing, right? So then there may also be the faster networking standards for cable networks and so on. But the idea is the internet will not just be exchanged overnight and saying, hey, cool, so we need new network cards, let's change the entire internet, so by tomorrow, by 31st, you only need to change your network cards, else you can't communicate on the internet. That's of course not how it works. So we need to abstract, that's why the abstraction point of view, we need to abstract on the lowest level from the higher levels that are standardized and will stay as they are largely for time to come. And even if not, they need to be compatible to competing standards. So those are the basic principles. So we have infrastructure, we have logical endpoints, so IP addresses, you like, and then applications on particular machines. But fundamentally, at the lowest level, what happens is that you have continuous, think about it like a continuous bit stream, right, that you're taking and you're chopping it up into individual parts, right? That's where the ones and zeros basically sit, and before they're then actually processed. And they are processed initially, of course, by your networking device, but then passed to the higher levels. And this chunking is basically done by having fixed signifiers. That's what we represent by the frame header, fixed signifiers that are characteristic for a particular network protocol. So if there are a particular signature, for example, stands for Ethernet, right? So it basically means that then the Ethernet card is able to chop up this continuous bit stream and knows, okay, this is the start of a package, this is the end of a package. Oh, this is the start of a package, this is an end of a package, right? It's very specific, predefined signature, standardized. And that's basically provides the basis for so-called frames, right? Chopping up the stream into frames that can be processed. Okay, now looking from bottom back up. With this as largely the entire structure, there's I cheated a bit, we get there. We have the entire frame, the frame header, and the interframe gap, which basically represents the frame and is specific to a particular network protocol infrastructure. Examples were again Ethernet, Wi-Fi. So sometimes you read 802.3 or 802.11 somewhere. No? Yes, perhaps. Well, you read it when you buy your next router. Whatever to read, and this is precisely referring to this idea. What kind of standard are we using there in terms of the packages that are transmitted? But then on the, if we come back to our email idea, what is the actual data? Well, the data is now contained here, and that is literally the actual the actual email information content that we want to get across. And that is specific to the email. What's the email format? What is it called? So what does it stand for?
Standard mail transfer protocol.
Simple?
Simple.
Yeah. So simple mail transfer protocol, right? So that's the idea. It's a very old standard from, I think 1987 or something. It's really old, this thing. Or at least based on that one. And the fundamental idea about how to send email. So in this package now, we have this email, hopefully in one or more segments. So if there are multiple segments, well, then there are multiple packages. This whole thing is called a packet, sorry. So you have multiple, but let's assume it's small enough to fit in one packet. Then we have the payload data there, SMTP protocol, and then we have this layer. What are protocols on this layer that we know or should know about?
TCP.
Yeah. What do they do, and what's the difference?
It's IETPs, for example. It's the protocol, for example, is for streaming videos. For example, it's if not all UDP signals get to the destination, is not that important.
Yeah.
It just tries its best effort.
Yeah.
But the TCP is best practice because it's best for sending text.
Yeah.
Because it tries to get everything to its system.
Or nothing. Yeah, cool. Yeah. So we have two protocols here that sit on this real transport header layer or transport layer level, and they are called TCP UDP. So I just repeat what you highlighted in the general fashion. But fundamentally differentiate into two types, right? One is really fast, the other one is not so fast. And why is the reason we have two? Well, it depends on the nature of the data you're sending, right? If you're sending data that needs to arrive, or at least, or in any case, arrive complete, for example, you're sending an email, you generally have the expectation that the email arrives or it doesn't, right? So, but not 50%, right? Or 75, or half of the email. That's weird. Yes, that would be awkward. So you kind of want it to arrive or not. And that is the strength of this TCP protocol. What it does is basically it chops up the data not only the data into packages into individual segments, but actually sends it to the target destination, but it ensures they actually arrive. So when a TCP packet is sent, it's sending information, expecting feedback from the receiving side to say, yep, I received this packet. Okay, cool, I'm sending the next one, and so on. And that's kind of continuous cycle until all those packets related to this payload are actually transmitted. UDP is the opposite. Well, so the advantage of this one, okay, reliability, of course, right, evidently. But why don't we just do it for everything? Then we have reliable receipt of everything we want.
TCP is slower. So, for example, if you want something that's continuous, or for example, or something, you would rather drop some segments instead of losing everything.
Yeah.
So you would, for example, if it gets a little pixelated, for example, losing some frames, but that is not that bad.
That's right. Yeah, absolutely right. So the point is basically it doesn't. It depends on the kind of application, right? If you're, for example, watching a stream, and we're doing that increasingly nowadays anyway, there's nothing worse by the disruption, right? We'd rather have a drop in quality. Also, we're tolerating more drop in video quality than in audio quality generally. So it's kind of important to bear in mind if you're dealing with streaming. But the thing is, we rather bear with a temporary loss in quality and pixelation and so on, and then recovery subsequent, than an interruption for example, waiting for a package for response. And the idea is basically there, it's a best effort approach. Whenever you stream something, you hopefully get most of what you actually want to watch. But if there's few frames lost left and right, or bottom, top, whatever, it doesn't really matter. It will not affect your experience significantly. Most likely you wouldn't even notice. But even if you do, it's faster to just forgo it than to resending those individual frames, because they may not be that relevant, right? So it really depends on the time of media. Same for music as well. There. So we have UDP and TCP. What do they actually stand for? Just to spit it out once and then forget about it forever. So who was first? I think you were waiting slightly more patiently.
TCP is for Transfer Control Protocol.
Yeah, and UDP?
User Datagram Protocol.
That's a weird one, right? So the name, but yeah. Yeah, that's right. User Datagram Protocol. Both correct. So that's the name of those things. So how do they look like? So it boils down to what kind of data you're sending here. If you're sending email, guess what? It will be TCP. If you're sending, what could be an example for UDP? Anyone?
Games.
A voice call.
Voice call is a good one. VoIP, yeah. Or games, yes. Games to some extent, right? When it's about synchronization data, then often you want to have TCP communication because you want to be, in multiplayer settings. But just for streaming, of course not. But voice call is a classic one. Just forget it. Doesn't matter, right? So if you have one dropped syllable, they will recover from this. But so how do those headers look like that I'm always talking about and never clarify what it actually is? Well, they look like this. That's an example. It would be TCP header that they look like. They have a fixed size, specified size. And the key things is that they always have some sort of addressing mechanism where they tell, okay, where is this header coming from? Or yeah, where is this header coming from and what is this time to? And particular to the TCP header is that it's specifying a so-called source port and destination port. What are ports? Anyone? The same crowd every time? Yes. Now it's your turn. Yeah, you're literally yours. Yes.
Well, on your computer, there's multiple programs running normally, and when you're sending the data to some server, that server might be running multiple programs, so it doesn't really necessarily know what program that is supposed to get that data.
Yeah.
And therefore, you when you send a packet, you specify the port you want to send it to. Normally, if you use like HTTP, you will use port 80. So if you want to connect to a web server, you port 80, and then that web server will get it relayed from the network or whatever. You also have to set ports on your own. So that the web server, when it sends back to you, it will know, your computer will know that this program will receive it.
Cool. Yeah, you covered most of the basics. The key thing about the ports was basically it's addressing within a given node, within a computer, let's say, right? So that's important to understand. Because intuitively you would say, hey, cool, I have my IP address, everything is sorted, right? So you can address my computer. Right? But the problem is, well, you have multiple services running, right? Or sockets bound generally on a computer. How many actually? 5, 6, 2? How many can you support?
60.
So yeah, we're converging on something here. I think that was the clearest number I had.
65,000 and something.
Yeah, it's specific. So 65,000 will do, right? So a lot. So there's potential for 65,000 and a bit more programs to run at the same time and use networking at the same time. So that's the potential we're talking about, just to get a feel. So that's an ample one. But okay, you still kind of need to know which ports are relevant for your particular package. Well, guess what? They're standardized. You alluded to some of them, right? Some of them are standardized anyway. You will always have the discretion to some, but yeah.
I think the first 32,000 are
reserved,
allocated to be standardized.
Yeah. Is it 2,000? I always thought it's 1,024.
Yep.
Right? That's the privileged ports.
So.
And then afterwards there's everything, no, convention plus everything goes.
You have 3 parts. The first 1024 is well-defined by IEEE or someone.
Yeah.
And then you have up to, well, I don't remember, like 16,000 are you can ask for them to be, you can use them in practice. And the last ones are just random. Just it's something your computer uses when it has to set a port.
Very good. Exactly. So, so out of those 65,000 port numbers and so on, again, the first 2,000 ones are really specified ports. The second ones are kind of by convention. So usually it's like products starting to use their own ports. What's a product's conventional port that is used by a product, you know, in databases, for example? There's one database, yeah?
Yeah, 3306.
3306, for example, the classic one. That would be a MySQL style or MariaDB style database, right? Anything that derives from this one, they always use that port, for example, right? So, or Microsoft's Active Directory, or I think use port 445 or something. So basically what those companies did, either they just took the port and it becomes kind of a convention, or they actually ask for it and say, hey, let's reserve this ideally for our product, and then people say, yeah, sure, well, works well. And before that, in those privileged ports, we have more general protocols. So what are examples for those ones that you guys should know about?
The first port or the third port?
The privileged ones on top, the ones that really don't change anymore. Yeah.
Port 80 is for HTTP.
Yeah, port 80.
Port 25 is for SMTP.
Yeah. So if you have a web server, you're most likely listening on port 80. What's the other port we need to know about nowadays as well? Because port 80 is a bit outlawed.
443.
Yeah, why is that?
HTTPS.
Yeah. So because most of the time you need to rely on HTTPS nowadays, right? So for development tool. And then we have mail. What port was that one? 25, right? So there also is a variant version and so on. So for database it's 326. So the point I'm making here is we may have different nodes and they have different potentially multiple ports on their respective machine. When you connect, your machine connects to a web server, for example, right? So www.ntnu.no. Well, it actually opens a connection. Which type of connection? UDP or TCP?
Which one?
Web.
TCP.
TCP, why? Why is it TCP?
Because usually a web server serves you files, so it's not possible if you get one. Just you want the whole thing.
You want the whole thing, right? So you just don't want half of the web page. You want the whole thing. So basically, it's a TCP connection. It opens from your machine to port 80. So that's specified. So when you do HTTP, which you will be doing as part of your mobile course anyway, then you're most likely opening a TCP connection to port 80. The system takes care of a lot of that carrying for you, but still relevant to know. On your side, however, your machine also open ports, and they sit above 16,000 generally, right? So if you, because the point is, if you're a client, you're not serving anything. 16.
It's actually 49,000.
49, that high? Okay, sorry. So let's put it in the mid-50s to be safe. Thank you. 5, 2, and so on. So the point is when you connect to an actual web server, so the destination port is port 80, you want to connect to www.intinu.com, well, you need to also give them a source port. And the source port is for telling the system whom to respond to, right? So you're sending out a request from your machine, right, to www.intinu, and eventually the request comes back, and you need to ensure that the application that lodged the request also receives the response, right? Your web server, for example. And that's done on your side. So basically your machine will also kind of open a port that awaits for this particular response. This is how the idea works on the machine level, basically. So if you have a given host, we get to the addressing of that in a second, then we have ports to kind of identify which services are actually talking to each other, right? My port 55022 is talking to port 80 on www.intinu, right? Because they may have multiple ports again. They may themselves offer multiple web services, or they may web services in general, but like, for example, database access point, mail service, and so on, or whatever else. So that's the idea, and that's how it all builds up. It says something about the sequence number. It basically says, okay, I'm packaged so-and-so in which particular order. It has a lot of different flags that signal aspects with respect to quality. It has a checksum of its own. So basically the idea is there, in order to ensure that the header is not corrupted, we need to have a checksum of the header in itself. So that's a checksum of the next of the payload, sorry. So basically to ensure that the payload is not corrupted, a checksum is calculated and put into the header. So on the receiving side, it's very easy to see if the checksum, think about a hash function, for example, still is identical, right? So we know that the payload is not corrupted in the process. That's how you would detect data corruption on the path. In which case, the package, for example, would be discarded, and you'll say, "No, it never arrived. Please send the same package again." Right? So that's about the reliability thing. So that's the TCP header. But more than knowing about this, now let's have a look at the UDP header. That's slightly more concise, right? So we see immediately that there's quite a difference in terms of functionality. So we still have this source destination port thing. Guess what? If you want to watch a YouTube stream, it still needs to know where the information is coming from, where it's going to. Granted, we need this. It says something about the length, how big is the payload that I'm sending, and again the checksum. That's it, nothing else. Right? So no acknowledgements, no flags, no further quality assurance, whatever. So it's really best effort. So it's really about as lean as you can get it as a header, and it's really about fast sending. So that's the main point of UDP. So if it doesn't arrive, bad luck. If it arrives, good. That sounds good, but no guarantees. So this is the navigation on the individual machine or host, on the node, if you like. On the next higher level, well, we have just been talking about how the communication works pretty much within a particular, or between particular services on a given node, but how the addressing of the nodes work is another aspect that we need to discuss. And this is classically resolved in the IP protocol. What does this thing do? Just for repetition. You guys mentioned it already implicitly, but let's bring it out again. Whoever.
The network header, I suppose that's a compression of the IP, the network layer and the whatever.
Yeah.
But the IP addresses are simply the ideally unique identifiers for each host.
Yeah.
Of course, this doesn't work because IPv4, which we all know is like the 192.168.0.1, they only allow 4 billion IP addresses. But anyway.
Yeah, that's a different story. Yeah.
Yeah. So the IP addresses, they uniquely identify hosts. We hope.
So what they literally do is just to identify nodes, right? They're saying you have a machine, you enter in your system, you check if you want to actually look into your IP config or whatever else. You say, oh, my current IP address is 192.168.0. whatever, right? So could be really anything on that nature, but it's really about your temporary identification of your device in a given network, right? Because this IP is generally not static, meaning if you move to a different network, to enter new, use Ideroom, for example, it will be different. But that's the function of the IP header. And this is this is how it looks like by IP package. So if you send something else between different hosts, what do we need? Well, we need to specify some sort of version of IPv4, some quality related flags, but most importantly, of course, a so-called source and IP address and destination IP address, right? Where is it coming from? Where is it going to, right? So it's coming from, well, in this case, 192.168.0.1, and it's going to NTNU's mail server IP address, basically, right? So, and this is then followed by the next higher level protocol content. Basically, the transport header, the one we just discussed, is payload to this one, right? And encoded, embedded in there. So on this layer, we don't know anything about the services that are provided by a given host. We just know, go to that host, and then the transport header will figure out which of the many sockets that 65,000 actually are relevant here right now on that particular target host. It's just to identify the machine. So we have source address, target IP address, and certain properties that are related to the delivery that are discussed there. This is, you pointed to IPv4 as one of the key points, but the IP protocol, and oftentimes we hear about TCP/IP in conjunction. It's actually conflating protocols across different levels. This is kind of the main point of convergence on the internet, right? When we talk about internet, we generally mean IP protocol, internet protocol, because this is where everything gets condensed down to in terms of standardization. It's a bit. So if you think about communication via the internet, we have a bit of a problem of diversity, right? On the lowest level, we're dealing with a wide range of different devices, Wi-Fi, wireless, cellular networks, blah, blah, all the stuff we talked about, let alone infrastructure stuff. So here's quite a bit of diversity. And on top, of course, as well, because this protocol needs to be generic to solve about any application you can think of, right? So applications you don't know about yet, that only come out in a few years and so on. But nevertheless, these protocol, I think from the, I don't know what the latest standard is, but for IPv4, but this protocol still needs to be able to be as generic enough to support all this. It also needs to be able to accommodate all the new devices that will be coming out in the future and so on. And that's why it's kind of the point of convergence. Everything kind of should be able to be reduced to IP, so then it can be openly communicated on the internet. That's the main point. So just important to bear in mind. But fundamentally, it's about addressing endpoint, a mechanism of addressing endpoints. So in the lowest level, again, I'll just bring back this idea here. It's really about network access only, right? So looking down here on this side, we can be dealing with Ethernet, Wi-Fi, WIMAX, GSM, Edge, of course 4G and now 5G and so on. I think they have started planning on 6G already, whatever that will be. We'll see. So you see all those diversity, and many of those acronyms you will never have heard and hopefully need to never hear again. But actually, some of them specifically related to mobile devices, of course. Did Mahesh give a talk about those? No? Okay. So there may be some discussion about the different properties of those networking protocols. But the point is, again, the important thing to take away here is those can change again over time, and it shouldn't matter. Yeah? So they're just abstracted away as long as they all are able to be converged and carry IP-based packages. Just looking at one example of those headers. Again, now there's many of them, of course. Is the one for the Ethernet. So that's the conventional cable network communication that we're using, for example, here. Generally referred to as IEEE 802.3. So the 802 series is basically all Ethernet-related standards that you will find. So 0.11 is Wi-Fi, 0.3 is this cable-bound one, and there's some other often experimental substandards in there. But fundamentally what this contains is, of course, a lot of meta information, but there's two bits of information again. We talked about the fact that all those packages are about addressing. And what are they addressing, please?
It just says like 2 octets or something. What does it mean?
Sorry, which one?
Like if you check like the second, there's like 2 octets, 4 octets, 6 octets, 1 octet, 7 octets.
under, like, there's a layer and then...
Right. They specify just the size of the respective parts. So basically, each of those headers is basically fixed in size. That's a fixed frame. And say, okay, hang on. The first 7 are reserved for the preamble, right? So then there's one left for the start of the frame. So basically, you're on the parsing side. Whenever you receive such a package, you follow the standard and operate whatever this frame off, and then you can re-identify. Okay, from octet 8 onwards, that must be MAC address.
But is 1 octet 8 bits?
Yeah.
Okay.
Oh, sorry, yes. Yeah, I don't know, but I use this term. Yes, basically it's octo. That's for age, basically, right? It's the same word. Basically, it doesn't matter. So.
8 bits, wait, 5. So like it's like a
bit.
5.
Bit.
Oh, right.
Yeah. So, but good point. So from the 8th bit onwards, that would be, for example, a MAC address, right? And then 6 further, there would be there would first be the destination MAC address, so where something is sent to via the wire within the room. So assuming you have machine 1 and machine 2 being plugged in, and you don't want to think about IP at that stage, but just the physical connection, then your machines will have unique identifiers coded into the network cards. You can potentially override this, but fundamentally they're attached to your hardware. They are provided by the vendor itself, by the manufacturer. And based on those those MAC addresses, the communication then can happen between those 2 machines that are connected. But fundamentally, the idea is that following the standard, if you work it through, you will be able to identify, okay, bit 8 onwards is a destination MAC address followed by the source MAC address and so on, right? So, and then as again, we have a checksum that basically checks whether the frame is complete in terms and no data is corrupted. And then there's, for example, here the inter-packet gap. So the idea is there's 12 bits reserved for just to delineate the gaps, so to ensure that you have a frame, a clearly separated frame, right? So to ensure that you cut this stream into unique information. Okay, I'll leave it. What's the time now? Oops, you probably deserve a break, I suspect. Yes, you get your break. And let's say 11:20, sensible, 8 minutes. And then I get slightly more practical.